Okay, today we're going to look at the last two trigonometric function graphs, the tangent and the cotangent graphs. And we're going to continue using our knowledge of transformations to help us out. So to get started, let's start with our knowledge of the unit circle. I'm going to label my quadrantal angles. Okay, so labeling my quadrantal angles over here for and to find tangent, we will call that tangent is equal to sine divided by cosine. So if I want to find the tangent of, say, 0 degrees, that would be my sine of 0 divided by my cosine of 1, which is 0. So we have the point 0, 0. Now, if I do the tangent of pi over 4, pi over 2, sorry, I get my sine, which is 1, and my cosine, which is 0. 1 divided by 0, well, you can't divide by 0. That's undefined. How do we deal with undefined? That becomes a vertical asymptote. And then for pi, 0 divided by negative 1 is 0. 3 pi over 2, negative 1 divided by 0 is undefined, so that's an asymptote. And then 2 pi, of course, is 1 divided by 0, which is still 0. Let's do negative pi over 2. So that gives us negative 1 divided by 0, so that's an asymptote. And then 0 divided by negative 1 is 0. And for a negative 3 pi over 2, that is 1 divided by 0, so that's undefined. And for negative 2 pi, that's 0 divided by 1, which is 0. Well, that didn't tell us a whole lot. So I'm going to try another angle for my unit circle. I'm going to choose 45 degrees, pi over 4. I know this is square root of 2 over 2 and square root of 2 over 2. And the reason I chose that is because, remember, tangent is sine over cosine, and these have the same sine value and cosine value. So square root of 2 over 2 divided by square root of 2 over 2 is just 1. So at pi over 4, which is about halfway between 0 and pi over 2, I have a value of 1. Now, in quadrant 2, remember my x is negative, my y is positive, so this is going to be a value of negative 1. Oh, sorry, value of negative 1. And then in quadrant 3, it's negative and negative. Negative divided by negative is positive, so that's going to give me a value of positive 1. And in quadrant 4, my x is positive and y is negative, so negative divided by positive is negative. And if I do the same thing for the negative angle measurements around, I get the following points. And so now we can start seeing a shape form. And it looks sort of like the x cubed graph a little bit. It curves up toward the asymptote, and it curves down toward the asymptote. And you find that curvature if you do some of those other, if you do like 60 degrees and 30 degrees, you'll see more of that curve shape. But this is the basic kind of graph of the tangent function. Notice it's still periodic. It's repeating the same kind of curvature over and over again. So we need to identify the period of this function. Well, I notice that from asymptote to asymptote, I see the shape, and then it repeats again and again. So this would be one period of my tangent graph, and from pi over 2 from negative pi over 2 to pi over 2 would be that period, and that's a period of pi. So all the other trig functions that we've learned so far, the parent function, the period had been 2 pi. Tangent's period is only pi, so don't get that mixed up. Now let's talk about some of these key things. So we know the period is pi. Next thing we want to do, I usually ask you to find the amplitude, but if you remember, our definition of amplitude was the distance from the midline to the maximum of the graph, or half the distance from maximum to minimum. But this tangent graph, these arrows mean that this continues on forever down and forever up. So it doesn't have a max or it doesn't have a minimum. So a tangent graph has no amplitude. It has no max or minimum. Now, for helping you on the terms to graph, if this had had a maximum, and we looked at our equation of y equals tangent of x, notice our a in this problem is 1. And look at this halfway in between my, halfway between 0 and pi over 2, we have a height of 1, that distance of 1. So although the tangent function does not have an amplitude, I will put this amplitude in quotations because it actually tells you the vertical stretch of the graph. And so instead of changing the name to vertical stretch, I just kind of do what's the A telling us? And that's telling us that we're going to have we're going to have a stretch of 1. But again, tangent does not have an amplitude. And because the midline is the distance halfway between the max and min, there is no midline. But to help us again, just to help us in our construction of these, if you notice, this is where all the transformation is going to go around, or that's sort of like it's like the midline of the function, because it's the center of that kind of curve. It's where the curves kind of meet. So that's something that's a little different. It doesn't have an amplitude, doesn't have a midline by definition. It does, however, have x-intercepts. So we notice our very first x-intercept is at 0. And then we have another x-intercept at pi and 2 pi, and then we continue on. So it repeats every pi distance. So to find your x-intercept, you usually find your first non-negative x-intercept, in this case is 0. And then you add the distance from that to the next 0. And so that would be a distance of pi. And then notice that that repeats every time. So to tell them how that's repeating, 1 times that pi by n, where n is an element of the integers. So that means I can multiply pi by 1, by 2, by 3, by -3, by -4, by any positive or negative whole number. So that's what the integers mean. So to write this in simplified form, we would just say n pi when n is an element of the integers. Now we're going to find the asymptotes. We're going to do this, sort of the same thing with asymptotes. Now these are vertical lines, so it's going to be x equals something. And you're going to identify your first non-negative asymptote on the graph, so that's pi over 2. So here's my first non-negative asymptote at pi over 2. Then we'll figure out the distance from it to the next asymptote. Now this one I can do in my head, but I take the next asymptote and subtract the asymptote that I'm starting with. And when you do that, you get 2 pi over 2 pi, 2 pi over 2, which is just pi. So I'm adding pi to get to the next one. And then I'm going to continue to add pi every time to get to the next one. So I'm going to add n pi. So I would say my equation of my asymptote is pi over 2 plus n pi. When n, of course, I've already defined n as an element of the integer, so I don't have to define it again. Okay. Similarly, we're going to look at the graph of the cotangent function. Now the graph of the cotangent function, looking at these special points again. Whoops. I'm just writing the same point over and over again. Let's try that again. 1, 0, 0, 1, -1, 0, 0, -1. Okay, and we already figured out that might not give us enough information. So we're going to look at this 45-degree point. In this quadrant, we're going to have negative and positive, negative and negative. In this quadrant, we're going to have positive and negative. Okay, cotangent on the other hand, now we're figuring cotangent x. That is cosine divided by sine. So the x divided by the y. Let me label my axes. Okay, so starting my quadrantal angles, 1 divided by 0 is undefined. So 0 degrees is undefined. Pi over 2, I have 0 divided by 1, so that's 0. At pi, I have -1 divided by 0, so that's undefined. At 3 pi over 2, I have 0 divided by -1, which is 0. And at 2 pi, I have 1 divided by 0, which is undefined. And I can do the same thing for the negative, with negative pi over 2, which gives us 0. Then we have undefined, 0, and undefined. So notice it's very similar to our tangent so far. Let's look at how else it changes. Okay. We'll start with pi over 4. So tangent, I take square root of 2 over 2 divided by square root of 2 over 2. So that does give us 1. So halfway in between here, we'll have a height of 1. Then in quadrant 2, we end up with negative divided by positive, which is a -1. Quadrant 3, negative divided by negative is positive, so we're at a +1. In quadrant 4, we have a positive divided by negative, which is a -1. So we see this time it's a decreasing function. So cotangent parent function is a decreasing curve, and this will continue on for each of these periods. Okay, so notice the similarities between the two graphs. It's just kind of shifted over and kind of looks like a reflection almost. All right, so how long did it take us to see one full picture of this? That would be still pi distance. So cotangent's parent function has a period of pi. Again, it has no max and minimum, so there's no amplitude. So notice I didn't list it here. It has no midline, although we're going to use in quotations that what should be like a midline to help us on our sketching. When we get to the transformations, you'll see that in the next examples. Our x-intercept, our first non-negative x-intercept is pi over 2. And how long did it take me from this x-intercept to this x-intercept? Well, that's a distance of pi. So that's going to be plus n pi, where n is an element of the integers. And then what is my asymptotes? Well, x equals the first non-negative asymptote is at 0. And the next one is at pi. So I got 0 plus n pi, which we'll just simplify down to n pi. All right, so let's see how this applies in a real life situation. So we're going to do everything we've learned in the other videos on how to rewrite equations in transformation form. We have basically all the same transformations, except again, remember the amplitude and midline I'm putting in quotations because tangent and cotangent graphs do not have amplitudes and they do not have midlines by definition. So first thing I do is rewrite this by factoring out, still inside the tangent, but factoring out that 1/2 to get minus pi over 2. And so I realized that my period is my normal period for the tangent graph, which is pi, divided by my b. And so that gives me 2 pi is my period. I do not have an amplitude, but it's that 1/2. The a, which is 1, is what fills out if we have a vertical stretch or not. And so in this case, there's no vertical stretch. I also have no adding or no vertical shift up and down. So that means my midline has not moved. It's going to stay on the x-axis, my quote-unquote midline. Phase shift, I got minus pi over 2. So that tells us I'm going to the right, pi over 2. Vertical shift, again, there's none. Reflection, there's a negative, and for A is negative, so that tells me across the midline. All right, and then the asymptotes and domain and range we can do in a moment. But first thing I'm going to do is the count by. So I have 2 pi, and I divide that by 4, and that gives me pi over 2. So I'm going to count by my normal pi over 2, kind of doing on the graph here. I recall from my unit circle, or from my parent graph, that 0 degrees tangent is 0. So I'm going to do on this first graph here, I've already dealt with the period by changing what I'm counting by. There's no vertical shift, so I don't have to worry about that. There's an amplitude, the midline, there's nothing changed there. And I'm going to do the reflection across this. So I'm going to do those two transformations, the reflection across the midline and dealing with the period. I'm going to save this phase shift for my next one. So I'm not going to deal with the phase shift yet. All right, so normally again at 0, we're at 0 degrees. And so that stays at 0. Then our pattern for this is 0. And then the tangent graph goes up. So our first tick mark is 0. Our second tick mark is at 1. And then the third tick mark is our asymptote. And then we kind of repeat from there. So at pi over 2, I'm going to have a 1. At pi, I'm going to have an asymptote. At 3 pi over 2, it's going to be negative 1. At 2 pi, it's going to be back. So notice I got that full starting at 0 up and then asymptote down. Now if I go backwards, you can probably see a better full period of this graph. So I go to negative 1 and then an asymptote. So right here in the middle, you can see now that this vertical, whoops, that kind of pretty bad. That's kind of stretching it out. And we get that one tangent graph. This time it takes us 2 pi to see that tangent graph. And then if I go back over to this side, I need to be at a height of 1 and then 0. And there you go, 2 full periods of that. Okay, so I'm going to take this middle one, the one that you kind of fully see, and I'm going to do our shift right. And what I usually do to shift these right and stuff is I start with my asymptotes. If I shift my asymptotes, then I can remember the pattern. Okay, so I'm going to take this first asymptote, well, this negative pi asymptote, and I'm going to shift it to the right pi over 2. So that means it's now here. And every point is going to be shifted over. So at 0, I'm at a height of -1. Pi over 2, I'm a height of 0. At pi, I'm a height of 1. 3 pi over 2 is our next asymptote. And of course, that pattern just continues. I'm going to have a stretch out tangent. And there's our 2 periods of this tangent graph. Get my asymptote over here. Alright, so now we got to figure out our domain and our range. Oh, our equation of our asymptote. So our first non-negative asymptote is here at 3 pi over 2. So it's going to be x equals 3 pi over 2 plus, well, how long does it take us to go from one asymptote to another? So I see this negative pi over 2 and 3 pi over 2 labeled, and I can see that that's obviously, well, it's easier to see it up here, from negative pi to pi, so that's obviously a 2 pi. So plus 2 in pi, where n is an integer. Now, if you don't want to write where n is an integer every time, what a lot of students do at the very top of their worksheet, they'll just write n as an element of the integers. And then every time you use n, it's understood that to be what you mean. So you don't have to keep writing it every time. Oh, I wrote that in the wrong line. Okay, so that's my equation of my asymptote. Now to do my domain, my range. Domain is our smallest x value to our largest x value. But notice that every time we have an asymptote, our graph doesn't have an x value there. So our domain is going to be all real numbers except where we have asymptotes. Well, how do we write that? Just like we did for the secant and cosecant, all real numbers such that x is not equal to, and then our asymptote equation. Our range is the smallest y value to our highest y value. Well, because those arrows go down forever and up forever, it's going to be all real numbers. It's going to be our range. Okay, now we're going to look at the graph of y equals 1/4 cotangent of x minus pi over 2. So first thing I want to start is identify the period. So we take the normal period of cotangent, which is pi, and divide it by our b, which is 1 in this case. So looking at this problem, our period would be pi. Our amplitude is determined by a, which is 1/4. Now remember, amplitude's in quotations because our graph is not actually has an amplitude. The first thing, as you notice, I'm trying to get the scale done. So if my period is 4, I'm counting by pi over 4. My amplitude, I said, is 1/4, so I'll make my y scale. I could count by half, but I think I'm going to count by 1, just so you can see how this stretches it out. The graph really stretches out, but you can choose, you could have changed your scale to what you wanted. Okay, there's no midline, there's no phase, there is a phase shift, which there's no vertical shift. The phase shift is right pi over 2. I get that from what's inside the parentheses. And my vertical shift is what's none, so I'm not adding or subtracting anything to the fraction. There's no reflection. I'm not multiplying by a negative. And now to figure out our asymptotes or domain and range, we're going to start by sketching our graph. Now I'm going to first sketch y equals 1/4 cotangent of x. So I'm going to do everything but the phase shift in this graph. So my parent function of a cotangent graph has our first asymptote on the y-axis. So we're going to start by drawing that asymptote. And then our first tick mark is our amplitude up, and then on the midline, an amplitude down, and then asymptote. And that gives us one full period, in this case, pi distance. And notice how stretched out this is. It's very, very flat. Okay, we'll do the same thing and now I'm going to deal with my phase shift. Now, phase shift is I'm going to take this right pi over 2. Now, what I do is I start by moving my asymptote over. But let's get our labeling of our axes. So make sure you don't forget to label your axes on your graph. All right, so I'm going to take that asymptote that is at the y-axis and I'm going to move it to the right pi over 2. And that gives me my first asymptote here. Now again, my next tick mark, I'm an amplitude above my midline. Then I'm on my midline. Okay, now I ran out of room, so I'm going to go backwards. So I'm below the midline, on the midline, above the midline by amplitude, and then there's in my next asymptote. And then again, below the midline by an amplitude, and then on the midline. So connecting these together, you get our graph of our function here of y equals 1/4 cotangent of x minus pi over 2. And I've graphed 2 full periods of it. So our asymptote, our first asymptotes occurred at pi over 2, plus now the distance between our asymptotes is our pi, our period of our function, times n, because where n is some integer. Ooh. And our domain would be all real numbers except for x equals not equal to, oh yeah, I forgot, I wrote y instead of x equals on my asymptote. Did I say y when I said it? Hopefully I said x equals. And our range is all real numbers because you can look at the graph here and you see that I have all the y values going up and going down.